Welcome back, sixth grade research assistants. I'm your lead scientist, and today we're diving into a brand new explainer all about water. Now, if you look around, water seems pretty simple, right? You drink it, you wash with it, it randomly falls from the sky. But honestly, water is a total master of disguise. It is constantly changing its shape, its form, and its location. Today, we're going to unlock the secrets of how water behaves, why it seemingly just vanishes into thin air, and how it manages to travel all across the globe. So grab your virtual lab coats because we have a lot of investigating to do.
Okay, let's take a quick look at our lab schedule. First, the 3 states. Second, the magic of evaporation. Then, the sweating glass. After that, we'll build a pot and pot cooler, make some clouds, and finish up with saving our water. Let's get to it.
To kick things off, I've got a bit of a mystery for you. You know those huge puddles on the playground after a rainy morning? Have you ever noticed how they just disappear by the afternoon? Or what about when you sprinkle water on a super hot dosa pan and it suddenly vanishes with a massive sizzle? Or think about hand sanitizer. You rub it on your palms, and literally seconds later, your hands are bone dry. That liquid didn't just cease to exist, right? It had to go somewhere. But where? Well, that brings us to Section 1, the 3 states of water. To solve our disappearing puddle mystery, we first need to understand that water exists in 3 totally different forms, right in front of us. When it's solid, like an ice cube, it completely holds its shape. You can pick it up, toss it around, it's not going to flow everywhere. But as a liquid, it flows perfectly, taking the exact shape of whatever container you pour it into. And then there's the sneaky one. When water becomes a gas, which we call water vapor, it just spreads out to fill up whatever space it can. It's completely invisible, floating in the air all around us, right this very second. And what's so cool is that water doesn't just stay stuck in one state. We can change it just by messing with the temperature. Add heat to ice, and it melts into a liquid. Pump in even more heat, and boom, it turns into a gas. On the flip side, if you take heat away, cool it down, the whole thing runs in reverse. Put liquid water in the freezer, it turns into solid ice. It's kind of like how hot liquid candle wax turns back into a hard solid once it cools off. All right, moving right along to Section 2, the magic of evaporation.
So, with that basic science under our belts, let's pull on our lab coats and look at how liquid water actually pulls off that crazy disappearing act on the playground. The secret here is a process called evaporation. Basically, evaporation is when liquid water transforms into that invisible water vapor gas. And here is the wildest part. It does not need to be boiling hot for this to happen. Evaporation is literally happening all the time, even just at normal room temperature. You actually see this every single day, like when you mop the floors, hang wet clothes out to dry, or feel that weirdly cool sensation when hand sanitizer evaporates off your palms. But here's the thing. Evaporation doesn't always happen at the same speed. Imagine we do a group experiment right now. We pour the exact same amount of water onto a wide steel plate and into a tiny, narrow bottle cap. What happens? Well, the water on the wide plate is going to disappear way, way faster. Why? Because evaporation only happens at the surface. So, a bigger exposed area means way more water molecules are touching the air, which lets them escape into vapor much faster.
And we can totally test other conditions too. If you put one bottle cap of water in the hot blazing sun and another in the cool shade, the one in the sun vanishes first, because heat rapidly speeds up evaporation. This is exactly why your laundry dries incredibly fast on a hot, sunny, or super windy day. The wind literally just sweeps the water vapor away. But if you compare that to a humid, rainy day, well, the air is already totally stuffed with moisture. It's like a crowded bus. There is just no room for any more water to get on, so your clothes are going to dry really, really slowly.
Next up, Section 3, condensation and the sweating glass.
Okay, ready for another mystery? Let's figure out why cold drinks always seem to sweat. You know the drill. You grab a freezing cold glass of lemonade and suddenly the outside is dripping wet. Now you might think, oh, the glass is sweating, the water must be leaking through. But our textbook friends Azavi and Thirov actually tested this. They put a completely sealed glass of ice water on a highly sensitive digital scale. If the water was just leaking from the inside out, the total weight wouldn't change at all, right? But guess what? The weight actually went up, which perfectly proves the water isn't seeping through the glass. No way. That water is arriving from the outside. So what's actually happening is all that invisible water vapor floating around in the air, which we feel as humidity, crashes into the freezing cold surface of the glass. Because the glass is so cold, it literally steals heat away from the vapor. And remember our rule about cooling? That invisible gas cools down and immediately turns back into liquid droplets. This whole process is called condensation. It's the exact same reason you wake up and see dewdrops on the grass on a chilly morning. Let's check out Section 4, Building a Pot-in-Pot Cooler.
Now let's take all this amazing science and actually use it in the real world. Specifically, how we can use evaporation as a DIY refrigerator. Avi's mom bought a traditional earthen matka pot for their drinking water. Now, unlike a shiny stainless steel pot that totally locks water inside, earthen clay is actually extremely porous. It's full of microscopic holes. So the water inside slowly seeps out to the surface of the clay and evaporates into the air. But here is the magic trick. Evaporation requires heat energy. So as that water turns from a liquid into a gas, it quite literally pulls the heat right out of the pot, leaving the drinking water inside refreshingly cold.
And we can totally build an electricity-free fridge using this exact same principle. It's so cool. You just take a large earthen pot and put a nice layer of sand at the bottom. Then you place a smaller pot inside that one and fill the gap between them with more sand. Soak all that sand with a bunch of water, pop your fresh veggies into the inner pot, and toss a wet jute sack over the top. Now watch the science happen. As the water evaporates from the wet sand and the sack, it continuously sucks the heat right out of the inner chamber. It'll keep your fruits and vegetables crisp for days. Absolutely zero electricity required. All right, let's scale things way up. Section 5, Making Clouds and the Water Cycle Journey.
For this next investigation, let's jump from a single clay pot all the way to the entire Earth's atmosphere. Did you know you can literally make a cloud in a bottle? It's true. If you take a closed plastic bottle with just a tiny bit of water inside, drop in a small piece of burnt paper, and start squeezing the bottle, you perfectly mimic what happens up in the atmosphere. When you finally stop squeezing and release it, the air inside rapidly cools down. All that invisible water vapor suddenly wants to condense, but it desperately needs something to grab onto. That is exactly where the smoke from our burnt paper comes in. It provides these tiny, invisible dust particles. The vapor quickly condenses around that dust, and boom, a hazy mini cloud forms right there in your hands.
Which perfectly sets us up for the grand epic story of water. If we follow this timeline, we can track the ultimate commute of a single water droplet. Picture our little droplet starting out in the massive ocean. The hot sun beats down, heating it up until, yep, you guessed it, it evaporates, shooting high up into the atmosphere as an invisible gas. As it travels higher, the air gets colder and colder. Our droplet slows down, condenses around a random speck of floating dust, and joins millions of other droplets to form a huge fluffy cloud. Eventually, that cloud gets way too crowded and heavy, and our droplet plummets all the way back to Earth as a heavy raindrop, or maybe even a snowflake. It hits the ground, soaks in to become groundwater, and slowly flows back to the ocean to do the whole thing over again. Finally, Section 6, Saving Our Precious Water. Now that epic cycle has been keeping our planet alive for literally billions of years. But our final lab discussion today is a bit more serious, focusing on our personal responsibility to our communities. See, only an incredibly tiny fraction of all the water on Earth is actually fresh water that we can use. Almost all of it is salty ocean water. There's this piece of ancient wisdom from the Theocoral that hits the nail on the head. If it does not rain well, even the mighty ocean will be drained. As the human population keeps growing everywhere, the demand for fresh water is absolutely skyrocketing, which leads to some really severe shortages. We absolutely cannot take the water cycle for granted anymore, and we have to fiercely protect our lakes, our rivers, and our groundwater from getting polluted. Which brings us to the end of today's explainer and to your final assignment. Remember, water is our responsibility before it is our right. I want to leave you with this really vital thought by brilliant 6th grade researchers. What is one everyday habit you're going to change today to help conserve our most precious resource? Are you going to finally turn off the tap while you're brushing your teeth? Maybe you'll set up a bucket to collect rainwater for your plants. I want you to really discuss this with your classmates. Oh, and for a fun extra challenge, try designing your very own board game that tracks a single water droplet through all 3 of its states. All right, until next time, stay curious and keep experimenting.